All right, y'all. So today we're going to be going over energy. Specifically, this is going to be the first in a three-part energy series because I don't want one like 40-minute long video. So this first one's mostly going to focus on kinetic energy. But before we go into that, I'm just going to talk about energy on its own for a bit. So the first thing is energy is described as the ability to do work. Now, that can be the thought of me picking up my pen and moving it around, throwing something, but that also can be thought about as particles moving back and forth, colliding with each other. It can be bonds breaking and releasing light, or bonds forming, such as things like fire or even nuclear explosions. Everything that moves, everything that happens, energy is going to be tied in somewhere. And so we just kind of think about that as the ability to do work, do something. Even the light heating up your body when you stand in the sun, that's energy being transferred around. So the first thing about energy is we have a unit for it. We usually measure energy in joules. Now, the unit for joules is J, and like most units, this is actually derived from a bunch of smaller units in our system international or SI unit system. And a joule is really made up of kilograms times meters squared divided by seconds squared. And we're actually going to return to this definition a couple times just so you can see why we use it and how it kind of makes sense. Now, we're going to focus on using joules more than anything, especially in this series, but there are some other units of energy. The first one you may know, so let's just do other units. The first one you may know is on the back of every food label package that pretty much exists. And so that's going to be a calorie. Calorie. Now, a calorie is simply described as the energy needed to heat 1 gram of water 1 degree Celsius. And a calorie can be shortened to CAL. And finally, 1 calorie is equal to 4.184 joules. So it's a bit bigger than a joule, about 4 times bigger. And that's probably one of the most common ones you might know. A little less common would be an electron volt, or what we can shorten to lowercase e, capital V. And 1 electron volt is going to be equal to 1.6 times 10 to the negative 19th joule. So it's much, 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 much smaller than a joule. And lastly, the third one that we may talk about is known as a kilowatt hour. Now, if you don't own a home or pay your own electricity bill, you probably have nothing to do with this one, which, by the way, this is KW-HR. And 1 kilowatt hour is going to be equal to 3.6 times 10 to the, times 10 to the 6 joules. It's much bigger than a joule. If you pay an electricity bill, this is usually what they measure your energy consumption in. So when you use electricity, you're using electrical energy, and you just get that billed to you by the kilowatt hour, essentially. So these are the main units, but I just want to reiterate, we're going to mostly focus on our joules right over here. Now, a couple things about energy is one way that I think a lot of us think about it is in heat. That energy we kind of sometimes measure in heat. If particles are moving really fast, it's usually hotter. You may even think about this as if you're running really fast. So we can talk about heat for a moment. So if you're just walking along, you're kind of walking slow, you're fine. But if you break out into an all-out sprint and you're just running super fast, sometimes you get hot. Now, your cells are pumping out a lot more energy, and there's a lot of reasons why you get hot, but you can kind of think of heat as faster movement. And one of the reasons we can think about that is because, like I said, with heat, or specifically with temperature, this is measured by the average kinetic energy. And this is kind of what we're going to focus on today. This is the average kinetic energy, specifically of particles. Now, this is where I take a quick diversion into, well, what is kinetic energy? So I'm going to go ahead and just take this out. And honestly, this whole section is going to be diversion on diversion. But let's take our little aside. Now, the first thing to do is break up the word kinetic. Kinetic generally means motion or movement. And so kinetic energy is the energy of moving things. We actually describe kinetic energy, or KE, as being equal to 1/2 mass, so mass of whatever is moving, times the velocity of whatever is moving squared. So if you take a ball and you throw it slowly, it doesn't have so much energy, but if you throw it really quickly, it has a lot of energy. But specifically, we are talking about kinetic energy, because kinetic energy, once again, is going to be the energy of motion or moving things. And it's all dependent on velocity. In fact, because velocity is squared, velocity is the most important factor of this equation. The higher the velocity is, the much higher the energy is. That's kind of what happens when you square a unit. So we're going to go ahead and within this kinetic energy sidebar, we're going to do an example. So in this first example, if we take our running person, and let's say this person weighs about 50 kilograms, and they're running at a speed of about, let's say, 3 meters per second. That's pretty fast, I think. I'm not sure. So our velocity is 3 meters per second, and our mass is 50 kilograms. Now, I want to point out something really important. Kinetic energy over here is going to be measured in joules. And so if we're going to measure kinetic energy in joules, then we need to make sure all our units work. Now we know joules is kilograms meters squared over second squared. So I'm going to go ahead and look at my units, kilograms, meters, and seconds. And I'm going to kind of plug just my units in and look at this. So we have mass, which is kilograms, and we have velocity, meters over second. But the important thing here is, remember, velocity squared, so this will be kilograms per meter squared seconds, or times meter squared per second squared, which is in fact the units we want. So it's good. So one thing that we need to know is that when we are measuring kinetic energy, our mass must be in kilograms and our velocity must be in meters per second, so that everything works out. Otherwise, we cannot measure our kinetic energy in joules. So that was a lot of information right there, but let's go ahead and solve our problem anyway. So kinetic energy is equal to 1/2 our mass of 50 times our velocity, 3 squared. And I'm going to keep my units in here, actually, meters per second. And this turns out that we get 1/2 times 50 kilograms times 9 meters squared per second squared, which will total out to 25 times 9, still keeping my units, kilogram, meters squared per second squared, which will total out to 225 joules of energy. So our kinetic energy of our moving person is 225 joules. So they're running really fast. That's a lot of kinetic energy right there. All right. I'm going to go ahead and end this little kinetic energy sidebar and move back into temperature, mostly because I want to. So temperature, once again, is going to be defined as the average Ke of particles. And the unit we measure it in, the unit, specifically the SI unit, is Kelvin. Now, usually you think about maybe degrees Celsius or degrees Fahrenheit, whether or not you're using the metric system or what Americans use. But in science, we like to use Kelvin, which is denoted by a capital K. You'll notice we do not have a little degree sign. Kelvin is just Kelvin. So something that's some temperature Kelvin could be like 273 Kelvin. So with that said, which is coincidentally 0 degrees Celsius, let's go into a couple things about Kelvin. Now, Kelvin as a unit is really useful in that it's actually based off absolute zero. Now, absolute zero is when Kelvin is equal to 0. So when the temperature is 0 Kelvin, that is absolute Kelvin. But the thing about 0 Kelvin is that, or absolute 0, is that there is 0 kinetic energy. So nothing is moving. That's our second point. No particle movement. This includes the electrons and the protons, which normally are always moving in every atom, but at 0 Kelvin, they're not even moving. Nothing is moving. And the last thing about absolute 0 is you cannot go lower. So absolute 0 is pretty much unattainable. And this is pretty much the end of the educational part of the video. If you want to stick around for like 2 more minutes, I'm just going to explain some dumb, stupid stuff that I like about other temperatures that are based off other systems. So while Kelvin's based off absolute 0, oh, here's where you can stop watching. Well, Kelvin's based off absolute 0. We have our 2 other ones, degrees Fahrenheit and degrees Celsius. Now, degrees Fahrenheit is based off something really, really dumb, and this is my own opinion that I hold. But why would you ever base something off something that's unchanging or something that is changing all the time? And that thing that degrees Fahrenheit is based off of is the human body. Because we're about 100 degrees Fahrenheit. Wow, that's really dumb. Because guess what? We're not 100 degrees Fahrenheit. And people change. If you have fever, you're over. If you're cooler, you're under. And it's something that's inconsistent. Celsius, on the other hand, that's a great system. Celsius is based off of water. And at 1 atmosphere of pressure, so that's standard pressure, like what you are at sea level, and with pure water, water will boil at 100 degrees Celsius. Wow, perfect. And it will freeze at 0 degrees Celsius. What a perfect system. It's based off 2 things that are constant things in nature that we can observe. Amazing. So there's my little dumb aside about how Fahrenheit's stupid, Celsius is better, but Kelvin, perfect. All right, have a great day, have a great night, and if you made it this far, I'm proud of you.